Hello my friends, welcome again to my video channel. Today we will finalize this project, the first step, and we will build a prototype of the high voltage power supply. But before we start the building of the prototype, we will have a short discussion about the final solution of the circuit, of the diagram, and of the PCB layout and of the construction. And now let's have a look at some components. Here we have some components on my workbench. A steel case with appropriate size. This will become the front panel. I have two analog meters here. Knob the pot is on my other workbench. The output connectors here and some small switches. I have to buy some switches which I think are necessary. This is the rear side with a heatsink. Here I will place the 4 output transistors, and here's some space for the cable and for the fuse, for the primary fuse. This is an experimental board. The distances between the pads and the drills are too small for 400 volt or 500 volt isolation, so I will remove these pads were not necessary to avoid any creepage and some isolation problems also. But in general I will use this board. It is good for the first purpose, and the later layout I will do with my CAD program, and we'll find a final solution. But the first version will be made on this board. It's a prototype, not more. I made a small mistake when I bought this case. I've overseen that the front and the rear side are of plastic. I'm not so happy with it. Here it is not a problem on the front side because plastic is a good isolation, and I will use also pots for the knob here with plastic. But the rear side, a heatsink on a plastic is not so good. My calculated full power loss will be approximately 100 watt, which could happen. High output current, full output current, 200 milliamps at, let me say, 50 volts, so we have a voltage drop of 400 volt times 0.2, this is 80 watt power loss. But this heatsink here has a thermal factor of 0.7 degree Kelvin or Celsius per watt, so we would have an increase of 60 watt. So the total temperature will be 80 or 90 degrees Celsius in case of full load for a long time. And the plastic is not the best solution, but for a prototype it will be good enough. So I will start first to finalize the circuit and then go to the mechanical construction. In the next step I will do a small experiment with a different connection of the transformer. The transformer we have seen is a little bit weak on the 400 volt side when you have 200 milliamp output, so the voltage drops a little bit. I will take my variac, my isolation variac, and connect it between pins 1 and 2. And this is a voltage doubler. This is connected to the center of the two capacitors here. The positive sine wave charges up this capacitor, and the negative charges up via this connection, this capacitor. So this is a voltage doubler, but only each half wave charges up this or this. So we need a little bit more power here. But the variac I have has the power, but it has not the voltage. It is limited to 260 volt AC or so. That is not sufficient. So I will take here now a voltage of, I think should be 170, 180 or so to get the 430 volt DC, but a little bit more stable with more power. It is connected to here, as you see, and the other end of the transformer is connected to the center of the 2 electrolytic caps. By the way, now I have removed the pot and replaced it by a pot with a plastic axis and a knob, so I have perfect isolation here. We see here the output voltage, input voltage. I will increase it to 450 volt. I hope nothing happens. No, the current is, the primary is 0. 315, no, it's okay. Let's go up to 450. Now we have 450 volt. On the primary side here, I can set the output voltage to 400 volt, that's the maximum. The pot is limited, the output voltage is limited by the 2 trim pots. And then I will increase the current shortly, as I had it to 200 milliamps. This is 2 kilo ohm, parallel 400 volt. That's 200 milliamps, should be back up to this value here, to the 20 here, the blue one. I have to be careful, only one hand. And now you see the output voltage is nearly stable. Much better now. That means the weak point is in the moment that the power transformer I have chosen, it's a little bit too weak. Okay, it is specified 120 milliamps AC, so totally 240 milliamps. And we have discussed it. It's a little bit too weak for the purpose here. But on the other hand, I don't see any problems with it. I don't want to generate power or to drive a power amplifier with it. It's only for testing tube circuits, and I think this is an acceptable result. And I have just seen that even my better variac is a little bit too weak. I increased the voltage to 470 volt. So now the output voltage is more stable because this voltage dropped a little bit too much. Okay, 398.6, 397. It's only 1 volt, a drop of 1 volt for 200 milliamps. So indeed, the weak point is a power transformer. Before we continue with the discussion of the last details in the schematic, I want to show you the different types of transistors. Up to now I've used this type, BUZ80, like this. This is, I think, not available any longer on the market, maybe old stock or so, but I had a lot of them in my box. But I want to use not this type here. The tab here is drain potential, and you know, we have there 450 up to 500 volt DC. When we screw it onto the heatsink, we have to isolate it. And be careful not to touch it, even when it is isolated. So the screw which is coming out on the rear side of the cabinet is maybe can get contact with the potential. Would not be nice. So I prefer this type, which is fully isolated. But this type only has 40 watt total power dissipation. This one has 100 watt, and I expect heat dissipation of approximately, when we say 300 volt voltage drop, 200 milliamps. This is 60-70 watt. So 2 of them should be theoretically sufficient, but this is an idealistic value which cannot be reached in practice. So I've decided to use 4 of them in parallel. And these are these types. It's a different one. What is it? One moment. SPA 11N80C3. I will show you on the schematic. I've got some of these. These are also rather old ones, but they have a good electrical isolation, you see, and the isolation is specified with 2000 volt DC or maybe 3000 volt AC peak or so. I will use these ones. Again, they have only 40 watts approximately. So I will use 4 of them to be on the safe side, and not only 2 of them, which would be theoretically sufficient. Well, That's regarding transistors. And now to the schematic. The MOSFET I wanted to use is the Infineon EPA80R1K4P7. It is available in April this year. I hope they mentioned this year, not next year. The obsolete type now I'm in the moment using SPA11N80C3. I could buy a bag of 50. The price is always less than $1 or €1 per unit. That's not the problem. The problem in the moment is the availability of semiconductors. You know the situation all over the world. So we have to take what we get. The requirements are not so big, so difficult. The isolation voltage should be 800 volt. And the rest is not so critical. This is the final schematic which I will use in my prototype. Maybe some resistors or capacitors will be a little bit tweaked in the value. In general, we have 4 transistors in parallel. Not this type. I will use, as I said, the other types. 100 ohms per source. Yes, you are reading right, 100 ohms. But the current totally is only 50 milliamps here per resistor, so the voltage drop here is only 5 volt. Not so big. Total voltage drop from here to here. So this is good, but it's necessary to look for equal currents in both transistors. Additionally, we have here another resistor, shunt, 10 ohms. So we have totally a resistance of 25 plus 10, it's 35 ohms. So the short circuit is limited to, when we say we have here 450 volt or so, divided by 35 ohms. This is a little bit more than 10. It's approximately 15 amp peak current, which is here flowing. That's okay. So we have a maximum voltage drop here of 150 volt, for which the whole system has to be designed. We have I will use 4 diodes, so the voltage here is limited to approximately 10 volt, with the full current flowing over these diodes. So we have not more than 10 volts. So the optocoupler here sees only 10 milliamps peak. That's okay for it. And here the ammeter, which has 1 milliamp and 1 kilo ohm, also is protected by this resistor, the diode. And here we have to use an external alignment. Another problem I found was the self-oscillation of the circuit. I had sometimes when I set certain voltages, some oscillations. This capacitor here between the output and the wiper, which goes to the gate here, blocked all oscillations. It's a negative feedback. That means when we have a positive wave, then this positive wave gets this transistor conductive and reduces the output. So this is a negative feedback, and any oscillations also are suppressed. This is also good to reduce the noise, ripple, and other effects on this line. I have chosen this connection point, not this one, because I don't know what happens here. Maybe there are some voltage peaks when connecting inductive loads or disconnecting them. So it could happen that over the capacitor the gate is destroyed. I have here a diode. But then the question is, which is stronger, the pulse coming in over the capacitor or the diode? And my experience is always the semiconductor loses such a battle, not the capacitor here. So I use this connection point here. It is very high ohmic, no problem, and the 100 kilo ohm protects this diode sufficiently. The Zener, sorry, not the Zener here. The rest is standard. We have discussed it in the output. I also use 2 capacitors in series. Shouldn't be necessary when we have not more than 400 volt, but worst case is that one of these transistors get conductive, are damaged, and the full voltage here is fed to the output via the defective transistor, and then we would here also have 400 volt or more. So I take 2 capacitors in series. Here is a negative output. This is a negative biasing of the feed here. I have a minus 72 volt chosen, 12 plus 60 volt. This parallel resistor here gives a little bit more current here in this path. Well, and this here is the output to the overvoltage, overcurrent protection. I will show you on the next sheet. By the way, I've forgotten to mention that this capacitor here for damping oscillations is exactly the same as we have here in the old Heathkit IP17. There's also a capacitor here from the output to the grid of the tube. And this C7 is it with 56 nanofarad SiC is the same here. I've chosen here 10 nanofarad, but maybe I will increase it a little bit. But it's the same principle. And in the output also a capacitor in parallel, which they have here also. Okay, these guys in those days also knew what they did. This is a second sheet, part 2, with the overcurrent protection. We discussed about it. I changed the circuit a little bit. This is now a variable shunt, 10 kilo ohm maximum, so the current coming from the emitter of the optocoupler, which represents the current in the high voltage side. I expect here 1 or 2 milliamps, causes a voltage drop here of 7.5 volt or more. Can be adjusted with this pot, so we have a trigger. We discussed it in the last video, not necessary to repeat it. I will now build up the prototype. I don't show you how to drill holes into plastic or metal housing, only some important steps, and then we come to the final prototype. Here we have the first mechanical approach to the prototype. So it's a front plate. The width is approximately 22 centimeters. The height is 12 centimeters. We have here 2 meters. One will become the milliamp meter for the output current. I've chosen these 30 voltmeters. It's easy to convert it to 300 milliamps. I only need some small labels. This will become 300 volt DC. I can switch it over with one of these switches to 600 volt DC. The other switch is there to measure the C- voltage. Full scale would be 150, so I have to take it 5 times, minus 5 volt DC. Pot for the B+, pot for the C-. Here the output, common, plus. There's a possibility to ground it. For grounding I will use such plugs. For example, with this plug, the minus is grounded. With this plug, the plus is grounded. If nothing is grounded, we have a potential free output. This is a C- output, and here we have 2 outputs, 6.3 volt filament supply. These 2 are isolated each other, 2 different windings, so I can add them in series with such a plug. Then I have here 12.6 volt. It's only necessary to look for the correct phasing. One phase orientation has to be in this one, and the other one has to be this one. If both are in the same direction, polarized, and when I would add it this way, then we would have here 0 volt. So it has to be in the way that we can add them. Okay, this is protective earth to the chassis. The chassis is metal. Here's a reset for the overcurrent protection with LED indication. The rear side looks like this. Now I will show you the, by the way, the pots here. The B+ is a 500K pot, and for the C- pot I've chosen 100 kilo ohm with a logarithmic characteristic. Logarithmic characteristic means that I can adjust the negative voltages in the range of 5, 10, 15 volt a little bit better, more precise than the higher voltages above 100 volt. Characteristic logarithmic is also used for AF amplifier setting the output level. Well, that's it. I will show you later in one of the next footages how to convert the sensitivity. We have a 30 volt, and as I understand it's 1 milliamp. That means we have internal series resistors. I have to remove them, and I will show you how to do this. But before I do this, I'll show you the rear side, the rear panel. This is a big heatsink. It has 0.7 degrees Celsius or Kelvin per watt. That means with 50 watt power dissipation we have a temperature rise of 35 degrees Celsius or Kelvin. Line cable, fuse, and here we have two fuses for the 6.3 volt AC output for the filaments. I fed these fuses also to the rear side because in practice this may sometimes happen that the filament is shorted and then the fuse is blown, and it would be a bad idea to have these fuses inside. This is the rear side. We have here 4 transistors, and as you see, for the transistors I have no additional isolation because I have the transistor type as I have set with full pack isolation, so I do not need any additional isolation. The white color you see around it, it's only the thermal compound, and it is no isolation. It had nothing to do with isolation, it's only the thermal compound. The heatsink, by the way, these screws are in a thread I have cut here, M3, so these screws are also grounded. These 4 screws here are installed in the same way. I have here cut the thread in it, 1, 2, 3 and 4. So when I threw the screws in, the screws have a secure electrical contact to the heatsink. It is necessary to have it because the heatsink has to be grounded. If anything happens in one of these transistors with a flash over to the heatsink, it is necessary to have a reliable grounding. So I have 4 pins and I will connect to ground all 4 pins, but only one. And additionally I will use these bolts here for a cover plexiglass also. That is the rear side. And now to the rest of the chassis. Here we have the power transformer. It has a diameter of I would say, let me measure it, 11 centimeter. It has a lot of windings. This is a primary side, 2 windings, 115 volt. I connected them together to have 230 volt. The others are the output for 2 times 310 volt. That is this output, red and blue. The other one are tappings at lower voltages, 280, 240 and 0, of course. Each has 120 milliamps, so we have totally 240 milliamps at 310 volt. This is not sufficient for 200 milliamps DC at 400 volt DC output. We discussed it. It's a little bit too weak as I have seen, but for the prototype it's okay. The other secondary windings are 2 times 50 volts, so I have 100 volt in series for the 140 or 120 volt C minus. The other is a 15 volt 1 amp and 2 windings 6.3. Here's the rear side, and I will bring together everything. This will be the final version, front, rear side. There's enough space for wiring, and the electronic itself will be on an experimental board, first version, which will be installed here in this way. So there's enough space for the components, for the big electrolytic caps, trim pods, and enough space for wiring here inside. So that's my first approach. And this is a cover, and I hope it will fit. Yes, seems to fit. This will be the final version. Don't touch it. It's dangerous. It will fall apart. That's a prototype, and now I will start wiring the experimental board. I've promised you to show how to convert these instruments to a more useful instrument. It has 30 volt and the internal resistance is 30 kilo ohms. As I found out, the movement itself has 2 kilo ohm, 1 milliamp, so we have 28 kilo ohm in series. and the series resistor is inside, because here is no series resistor installed. So we have to open the instrument. It can be done rather easily, unscrewing it. By the way, other instruments have the possibility to get access on the rear side, but here are no screws. These screws are these two ones. No, sorry, these are the inner ones we also have to open. But these two screws here, first remove the bezel. But it's necessary when you have other types to have access from the rear side. So this is only an explanation for this type of meter. So first we remove the two screws. Then we can remove the bezel. Nothing happens, and then we have the next two screws which fix the scale. And behind there is a series resistor. So we also unscrew them. No fear, nothing will be damaged as long as you are careful. And then you can remove this scale very carefully. And here we see the series resistor. This is 28 kilo ohm. I will now unsolder it. And then I have the pure instrument on the rear side of the connectors here. We need here big iron, because the connector on the rear side is rather thick and heat eating. Wow. Okay. That's it, and that's it. The movement moved a little bit, but it's not dangerous. As you see, this is a complete unit. It will be brought back in this position. And now I will connect the plus one to the red wire. Okay. And then bring back the scale and the bezel again. This is a little bit tricky. To find the hose again. But it's rather easy. The second screw also will find its place, and its thread automatically. There is a guard inside. Okay. Do not over tighten it. Then bring back the bezel and look for this pin here. The pin has to be located in the slot for the knolling, for the centering of the pointer. And that's it. Job is done. Same procedure with the other instrument, and now we will check the internal resistance of the meter and the impedance. And please, never measure the internal resistance of such a meter with an ohm meter. We can assume the sensitivity is 1 milliamp. Some of these instruments also have 100 microamps only, a fraction of a milliamp. And when you use a milliamp meter, ohm meter. The current is several dozens of milliamps or up to 100 milliamps and more. This would kill the instrument, maybe instantaneously. Never do it. Measure only the voltage drop at a known current. That is what we will do now. To check the parameters of the instrument, I connected the internal resistor, which is now external resistor, in series to the plus pole, minus pole, and I will connect 30 volt DC from an external power supply. And now we have full scale deflection. As we can see, when I remove it, we have 0. Connect it again. We have 30 volt. And now I can measure the voltages. First, the voltages. The input voltage should be rather exactly 30 volt. Okay, that's within the tolerance. And now I measure the voltage across the instrument from here to here. With the resistor we have 30 volt, without resistor we have a voltage drop of 230 milliamps. 230 milliamps. Millivolt. Good morning. 230 millivolt. And now I measure the current flowing into the instrument. It is expected to be 1 milliamp. But again, I will check it. Go to milliamp. Plug it in. Go to the power supply. And then connect it together. And we have a current of 1 milliamp. Exactly 1 milliamp. So we have these parameters of the instrument. 1 milliamp current, 230 millivolt voltage drop, so the internal resistance is 230 ohms. So it's important to calculate the series and parallel resistors for the annunciation of the milliamp and the volt for the ranges, and to calculate the setting ranges of the trim pots. This is the end of part 4 about our high voltage power supply. We have seen now how to construct the prototype. I have to do some alignments, some fine tuning in the schematic. There are some issues I didn't talk about, but some resistor values and capacitors and so have to be optimized. But in general, the schematic is ready. I will publish it on my website when it is completely ready and built and successful, so you can build it for your own. But this will be part of part 5. Stay tuned, stay healthy. See you on this channel.